Greetings and welcome, friends. Mr. Waddy here. We're talking about section 3.6 about translations and reflections, transformations of linear functions, where we're going to think about the different ways that I can have lines with slopes and different y-intercepts and flip them around and move them around. We're going to think about them as modifications of a parent function being f of x equals x, or just y equals x, just kind of the default linear function. And so a family of functions is a group of functions with similar characteristics. Today and tomorrow we're going to be talking about lines. All right, so they're all going to have a slope, they're all going to have a y-intercept most likely, things like that. And the most basic function in a family of functions is called the parent function, from which all of the other functions kind of derive their shape from. So for non-constant linear functions, the parent function is y equals x or f of x equals x. And the graphs of all other non-constant linear functions are transformations of the graph of the parent function. So if I modify this by stretching it and pulling it and flipping it and shifting it around, that's what I'm talking about when I say transformations. So a transformation changes the size, shape, position, or orientation of the graph. And so here, our first type of transformation that we're going to talk about today is a translation. All right, and a translation is a shift horizontally or vertically, but does not change the size, shape, or direction, orientation of the graph. Okay, so we've got two types of translations, horizontal and vertical, which in the world of lines, it's not that interesting, but we are going to do transformations on absolute value graphs in a couple of days. And in that case, it will be more definitive and distinct, where it's a little bit harder to see here. So for horizontal translations, the graph of y equals f of x minus h, meaning if I subtract some number from the x before anything else happens to it, they're saying is a horizontal translation of the graph f of x when h is not equal to 0. So if I had f of x minus some number like 3, this is where it's weird, right? Here's the positive x-axis, here's the negative x-axis. If I'm subtracting 3, it shifts it towards the positive direction. And if I'm subtracting a negative 3 or plus 3, all right, maybe I'll even write it like this, f of x plus 3, or over here, f of x minus 3. If I'm adding a number, it actually shifts it towards the negative side. So horizontal translations are kind of moving in the opposite direction that you would expect. But you can see that the parent function, y equals f of x, is here. And if I subtract 3 from its x value, it's the same line. It's just been moved over to this orange line. Or if I add 3 to it, it's the same line. It's just been moved over to this blue line. So subtracting h from the inputs before evaluating the function shifts the graph left or right. A vertical translation, notice the similarity here. The minus h was being applied to the input. Here this plus k is happening after my function is evaluated. So it's after everything has happened to the x. Then if I just say, oh yeah, take all your outputs and add k to them, that would result in a vertical translation of the graph where it shifts it up whenever k is positive. Right, so if I have f of x plus 2, it would have shifted the graph up 2 units. And if I have f of x, say, minus 2, it would shift the graph down 2 units. So adding k to the outputs shifts the graph down when k is negative and up when k is positive. So let's see if I can get a couple examples in here. Maybe we'll just get one. We'll see. We'll see what we can do. So here's example 1. All right, so I've got a function f of x equals 2x minus 1. All right, that's my original function. And they're saying graph a new version of that function where I add 3. This is afterwards, so this would be like my plus k version. This is going to be a vertical transformation. So regular old f of x equals 2x minus 1 would have had a y-intercept at -1 and a slope of 2, right? So up 2 and over 1 and up 2 and over 1. And I'll draw that line. And up 2 and over 1 and up 2 and over 1. Something like that would be my original function. Okay? And now if I want to add 3 to that, I'll make a new version of it. If I have f of x plus 3, that's going to be if I did 2x minus 1 plus 3. All right, after all of this was evaluated. Okay, and what does that simplify to become? That's the same as 2x. What happens when I combine these like terms? What's -1 plus 3? Positive 2. Yeah, positive 2. So I'll get f of x plus 3 outside the parentheses is the same as 2x plus 2. And we're also just calling that a new function g of x. So they've got all sorts of names flying around here. But I'm expecting that adding 3 would shift this up 3 units, and this up 3 units, and this up 3 units. And notice that is in fact what I would get if I graphed y equals 2x plus 2. It has a y-intercept at 2, and then up 2 over 1, up 2 over 1. And so this line is going to be parallel, and watch this. This is perfect. I can just drag this up, and then bam, it's a parallel line. It's just been shifted up 2. So vertical shift, vert up 2, right? Actually, I think I'll use the word up rather than plus. Vert up 2 is what happened to that function. So let's see, how about if I have f of x plus 3 inside the parentheses happening to x inside with priority. So actually, let me pick a different color. So f of x plus 3, that would be the same as if I had 2 times x plus 3 instead of x. Notice this, guys. See this? Look up here. Instead of x, I've replaced it with x plus 3, and then the minus 1. So you guys see the difference where this plus 3 happened afterwards versus this plus 3 is happening to the x before anything else happens to it. To simplify this, you could distribute. So that's 2x plus 6 minus 1, and 6 and minus 1 combined to be plus 5. So if I graph the original function, actually that should still be the same thing. So it originally has a y-intercept of -1, right? Let's see how well I can keep it parallel here. So there's the original function. And now this function, a plus 3, this is what's weird. It's plus 3, here's the positive x, here's the negative x. I'm expecting that to shift this 3 units to the left, right? And 3 units to the left, and 3 units to the left. Even though that's a plus 3, it moves it in the opposite direction for horizontal transformations. And notice that is in fact what I get, a y-intercept at 5. So 1, 2, 3, 4, 5, and then up 2 over 1, it will in fact give me that line. So even if I was to graph that using slope-intercept form, I would in fact, let's see, did I line that up really good? There we go. That's a little better. It is in fact a horizontal shift over 3 units. Every one of my points on the yellow line has been translated 3 units. Okay, so horizontal and vertical translations. Good stuff, good stuff. Let's see, I was going to do, maybe we'll just describe these functions right here, and that'll be the end of it. We'll just talk about horizontal and vertical transformations, which are called translations when we're just shifting it. Okay, so here's my parent function. Here is some new translation. What do you think minusing 2 on the outside does? Which way does that shift that? Up, down, left, right. Yeah, that's a vertical shift, so that's vertically down by 2, okay? Whereas if I have x minus 2 on the inside of parentheses, it's negative. It's going to shift it in the opposite direction that I would expect. So this is horizontal because it was inside the parentheses. And which way do you think it'll be? Right? Positive x is over here, negative x is over here. This will actually shift it right 2 units. So that shifts it in the opposite direction I would have thought, right? It moves it towards the positive x rather than the negative x. So I won't take the time to graph that. We'll just kind of analyze it in that way. All right. Well, thanks for watching, Internet friends. Have a great day.